Okay, so welcome back after lunch, everyone. So we are continuing afternoon session, and Vladimir is going to tell us about, Vladimir Dobrev is going to tell us about invariant differential operators from conformal symmetry to quantum groups.
Okay, thank you for the invitation to give this talk here. Actually, this subject is vast, and there are several ways to present the material, and I decided to start from something that everybody knows. Okay, the plan is big, but maybe it's not important. I was told by the organizers that at the end, the files will be on the web page. So whatever I would not be able to say, you'll find in the file after some time. Okay, so I start with something that everybody knows, and in particular, the Maxwell equations, which I give in three forms, in equation 1, 2, 3. And this, of course, this is something that you all know, and maybe I will not stop very much on this page. What maybe you don't know is that the equation 3 can be written as two conjugate scalar equations, phi A and B. Now, of course, there is I'm sorry for the mistake. There should be an index 0 here, which somehow. Okay, so this is because this is the notation for these operators. So as you see now, I have a lot of additional notation. I have the Minkowski variables combinations, which sometimes are used also by other people. And then the F plus and minus are these combinations which are given. Maybe 1 second.
Is Z the same as V?
No. Minkowski coordinates are denoted by X plus minus and V bar. And Z and Z bar are two additional variables. And they are now, until this moment, as bookkeeping devices. Now, these F plus and minus are second order polynomials in Z and correspondingly Z bar. J is first order polynomial in Z and Z bar. And then if you put this back into 5 and take the powers of the variables Z and Z bar, then you immediately get the Maxwell equations in the well-known formula 3. Okay, now you can ask, of course, so what of this? Now, what is the point is that these two operators, the plus and minus, are have group theoretical meaning. Namely, they are intertwiners of the conformal group, which of course means that they are, which certainly shows the conformal invariance immediately. And how to check the intertwining property, by the way. It is very easy. Now, DC plus minus, I rewrite once again into such form, where I use now three different operators, I1, I2, and I3. You see there's some vector field in the Minkowski variables, and then the Z and Z bar come with their own operator. And now this directly goes to representation theory. I just recall now something from representation theory. You have Verma modulus V lambda. Lambda is the highest rate. Everything can be done also in lowest rate, and in half of my papers it's lowest rate and the other is half highest rate. It doesn't matter, except when considering unitary representations. Okay, so this is of course the defining property of Verma of the Verma module. It has a highest weight vector, which is annihilated by the Racine generators, and scalar action by the cartons. What is nice about the Verma modules is that generically they are reducible, but of course the reducible points are the important ones which we need. And I recall the criterion of Bernstein-Gelfand, that the Verma module is reducible if there is a positive root and a positive integer, such that this numerical equality holds. Here rho is half the sum of the positive roots. Lambda is the weight, as I said. And then, if this holds, then the Verma module V lambda contains an invariant submodule V lambda prime. Prime is lambda prime is shifted weight. And, of course, this is next, that there is a singular vector V lambda, such which has similar property as the highest weight, but with the shifted weight. Now, restricting to the SL4 case, that was general, what I said above, we have the singular vectors of weights alpha 1, 2, alpha 2, 3, alpha k are the simpler roots. And this is, of course, a result which is just calculable in 1 minute. That these are the singular vectors of these weights, alpha 1, 2, and alpha 2, 3, where xk are the simple negative root generators. Now you certainly see the similarity with what I wrote here and what was termed the Maxwell equations. In order to make it, to put it even more explicit, is that you have to pass from generators to the right action on the coset SL4 over B, where B is a Borel subgroup, and this coset has local coordinates which are just these coordinates which I introduced, so to say, on the way. You see the four Minkowski coordinates, and the Z and Z bar and the Z and Z bar are also here. And then, of course, what the relations, the formula for IK, which I showed earlier, is immediately derived by just applying the right action of this the three simple negative generators. And now you see that the variables Z and Z bar, which I introduced as bookkeeping device, together with the Minkowski coordinates, have definite group theoretical meaning as the 6 local coordinates of this Fleck manifold. And in fact, this is in a nutshell is how we can derive any invariant differential operator corresponding to a Verma module. Namely, you take a singular vector, you pluck the corresponding right action. Of course, with different groups, the coset on what one is acting will be different, but the principle is there. Okay. Okay, so now, of course, we have to make a real connection with the representation theory, and that's why we have to remind that the four-dimensional conformal algebra, which was mentioned heavily in the first 2 talks, SU22, they are labeled by 3 numbers, N1 and N2. The first 2 are fixing the Lorentz, find the dimensional representation of the Lorentz algebra with this dimension, and this is the conformal weight. Some people call it conformal dimensions, some people call it conformal energy. It doesn't matter. And also, physicists sometimes may use this J1, J2, but that's not essential. And now the intertwining properties that I mentioned can be given in this diagram. Actually, I was talking about chi plus and chi minus, which are the components in which the Maxwell tensor splits on the Lorentz symmetry. J mu was also mentioned, but you have also see there 3 more representations, which are actually, of course, you have also knowledge. Of course, you can recognize that when you apply d mu to a mu, you'll go to f mu, and these are the weights. You see here the canonical weights for Maxwell tensor 2, for the j mu is 3, and for the a mu is 1. This you know very well. And now there is additional information on the picture. I said that these differential operators come from single vectors of weight 1, 2, or 2, 3. Now this one comes from a simple root alpha 2, and this one comes from the root alpha 1, 3, which is the sum of the 3 roots. This is the highest root of SL4. So everybody is in the picture. Yes. Now, actually, yes, all this picture with the same operators can be, okay, more general cases, can be generalized if you take this more general tensors. For instance, fk is a polynomial in ZZ bar of degree k plus 2 and k, and etc., etc. Now, if you want to write this with indices, the fk would be, maybe I have it on the next slide. Yes, I have it. Now, fk plus minus correspond to such tensors f mu, alpha 1, alpha k, where this tensor is antisymmetric in mu, symmetric in alpha, and traceless in every pair of indices, while gk corresponds to g mu, etc., etc. But the equations which work with the same operators are these similar operators where only there is some number k introduced there. Now, if you want to work with indices, you get a tremendous headache, because after action you have to symmetrize, anti-symmetrize, take out trace, and so on. Nothing to do here. It is just the same equation, only some coefficient is changed. And because getting very enthusiastic about this, I call these equations Maxwell hierarchy, and the Maxwell equations are the zero member of this hierarchy. Of course, this is a simple part of the general SL4 and also conformal diagrams. Now, as you can see here, again we have 6 representations. I'll give the signatures on the next slide. And here again we have the operators of weight. For instance, this is of weight n alpha 1 alpha plus alpha 2. This is of weight nu alpha 2. And this is of weight nu alpha 1 plus alpha 2 plus alpha 3. Here there is one very nice thing to say, that in fact this picture is also valid for other real forms of SO6, namely SO51 and SO33. In fact, the first time this diagram was written, we wrote it with value exactly for SO51. Only then it was also applied to SO42. And now I give you the signatures. Everything is absolutely explicit. So you see, this is the weights. This is the first two are the Lorentz, as I said, Lorentz dimensions. And the last number is the conformal weight. These are positive integers. Now there is a very more general statement. Actually, I'm talking about Verma modules, but I could have used also the language of elementary representations, and as Gerhard was using. There is one subtle point that for the group, if you want to work with the groups, there is also a signature which enters. But at these points, at these reducible points, the signatures are completely fixed, so we can omit to mention them. Of course, they are given in one of my papers. So if you're really interested, you can see this. Okay. Now, so as we see these representations, they come into such as sextets, and the reducible Verma modules occur also in some doublets. There are three kinds of doublets, which I omit for lack of space, but of course they are explicitly known and given in our papers already for the Euclidean case. And the sextets and the doublets exhaust all reducible Verma modules induced from finite dimensional Lorentz representations. It will be the Lambert equation, but it will come later. There is the Lambert equation all over, yes, but it comes later. Okay, you see. Yes, you see. Okay. Now maybe I didn't understand the question. Now, you see, certainly many of those representations obey also the Lambert equation, etc., etc. What I was saying is that these sextets and the doublets exhaust all reducible representations. I didn't say that all invariant operators are exhausted. They are there. And actually, there will be an example about this later in the lecture, explicit example. The doublets are obtained in a very simple way. This is something that mathematicians call going to the wall. And so, for instance, if you take this picture, say put nu equal to 0. Only two of these guys will remain sensible. This is the doublet. Because you see, they have to be Lorentz representations. You see, so it's very simple. Going to the wall, you get them. It's unavoidable. Okay, so now I jump a little because what I was saying was for SO42, SO33, SO51. What about SO-PQ? And when SO-PQ with P plus Q even, we have the same diagram. Only it's longer, but the structure is the same. And then you can say, what about the odd cases? Odd cases are simpler. These are the odd cases. These are the odd cases. Okay, of course. And if you're interested in the signatures of these guys, you can look into some of my papers. They are all there. Of course, certainly I had to omit here a lot of details, wanting to say more things. Now I'm going to introduce a class which I call conformal algebras. In the beginning, you see, since I wanted to apply this machinery for other algebras and to be more explicit, but then of course you have to work algebra by algebra. So what to start with? So I started with the Hermitian symmetric spaces. There is geometric criterion, but we need the algebraic criterion. Is that that the maximal compact subalgebra of the non-compact G, simple group G, must have this form. So it has a factor SU2, SO2 or U1, whatever, plus some other piece. Once you have this, then the algebra is the class of Hermitian symmetric spaces. These are the six families, 6 cases. These groups have highest, lowest weight representations and anti-holomorphic discrete series representations, yes. We already considered the conformal algebras, which which of course you know very well, this thing. And they have this, of course, very physical properties, this decomposition, which mathematicians call Brouillard decomposition, which Brouillard decomposition in the case of the Euclidean conformal group is given in great detail in the book, which was shown in the beginning of our conference. But here in the conformal case, it's nice that they have group theoretical meaning. This Lorentz subalgebra, dilatations, translations, especially conformal transformations. But what I'm interested in now is a special feature of the conformal algebra, that the complexification of the maximal compact subalgebra is isomorphic to the complexification of the first two factors of the Brouillard decomposition. And in particular, the coincidence of the complexification of the semi-simple cases, this is K prime, kappa prime was the piece from the maximal compact, and M is the complexification of the Lorentz. This coincidence means that the same representation, the finite dimensional representations unitary of K are the same, K prime are the same as the finite dimensional non-unitary representation of M, of the Lorentz. Now, it turns out that some of the Hermitian symmetric algebras share the above mentioned special property. This subclass is smaller. Of course, here, this was Mn, now this was PQ, now it's only PQ. This is only for 4 times P, and E6 disappeared. So I call this conformal algebras. This class was identified also by Gerhard Mack. He gave it another name, and he had other considerations about how to extract this class. But obviously, it's very important if and also Gunoydin had it, but I forgot even what he had in mind. Okay, so now I will give you quickly the main points about each of these cases. We start with SUPP. The maximal compact is U1, and this was given by Ivan Todorov for P equal 2. And now, the diagram, which I was showing, I can calculate. In this case, I devised a formula to calculate how many members will be in this diagram. And it turns out that this is 2p over p. You put p equal 2, you obtain 6. And we already had the sextets for SU22. But of course, here, it is bigger. And actually, it quickly gets out of hand. So I can show you only the cases p equals 3 and 4. P equal 2, of course, we considered. Now these diagrams these are also diagrams for SL2PR. And if p is equal to 2k, then there are also diagrams of SU star 4k. That's not very important, but just to know that the diagrams for SO42 was given also for SO51 and also 3. Also here we have these diagrams. Oh, there's something happened. There is some convention which I'll use. Yes. Since the diagrams very quickly get congested, I have to simplify the relation, and then this symbol ijk encodes the root beta jk and the numbers mi, which encode the reducibility conditions of the Verma module which I have given. Now for SU33 it's not so bad. One can even see some nice structure there. For SU44 it is already, yes, now we can understand why I cannot draw SU55. Even if I calculate by machine the representations, I would not be able to make such nice diagram. So let us pass to something easier. Okay, so now we pass to SP and R. That's really slightly easier. For instance, the number of representations is given by 2n, not by factorials as the other case. And I can even draw the cases 3, 4, 5, 6. N equal 2 I would not give. It was given as SO32. It is the same. And if any is even, then we can also have the same for SPRR. So SP3 is very simple. It's a little like one of the conformal ones, but there is different roots entering, and it cannot be the same in principle. Okay, so you see here things are going more complicated, but not so quickly. Not so quickly. Even SO55 is SO5 SP5 is good. SP6 now, of course, is, but still manageable. Still manageable. Yes. Okay. Now next comes the algebras SO star 2n. Here this work is not entirely finished. Of course, I have to, the class of the conformal algebras is when n is itself 2r, so I have to consider SO star 4r. And here the first non-trivial member is SO star 12, because SO star 4 is SO3 plus SO21, and SO star 8 is SO62. The conformal algebra is 6-dimensional space-time. Here the numbers correspond to the formula which I have given. There are only 32 of them. Only 32 of them. And this is how they are given here. So as I said, this work is not finished for the bigger ones. It is still work in progress. Okay, so now we have E7 minus 25. We have the signatures. We have the numbers. You see, here I have shown explicitly what to divide the two Weil groups. So the result is 56. And the diagram looks like this. Not so bad. Not so bad, yes, okay. So, okay, so of course we wanted also to see what is the difference when you are not in the class of conformal algebras. So I looked at the algebra, say E6 minus 14, which are not in this class. And here there is no formula like the formula I devised for the number of the representations. There are 70, should be 72 by that formula, it's not valid. And here it is, now you can see the picture is different. There was a symmetry in all of the diagrams. There was a symmetry with respect to a bullet which was written, and I didn't explain it before. Actually, the bullet actually has a very important property. For this, the bullet actually was showing the action of the Knapp-Stein integral operator. So every 2 points symmetric with respect to the bullet, which was in the other diagrams, was actually respected to these Knapp-Stein operators. They're also well explained in the book. Okay, here the things are different. Here the symmetry is according across the dotted line in the middle. So it is, this shows one crucial difference with the conformal algebras in this respect. Okay, so let me see how I'm going with the time, because now we'll start something more difficult. There is some time. Yes.
So this conformal algebras, is there some relation between the algebras and algebras of conformal Killing fields on some particular manifolds, in the same sense as SOT2 arises from the cylinder? Could you consider some other manifolds of the form some compact manifold times R, special compact manifolds, and get all of these conformal algebras?
This I have not studied, but very possibly, because the point is that they have the very similar structure. They are all induced by maximal parabolic subalgebra. Maximal means that there is all dilatations, which are one-dimensional. So maybe the answer is positive, but I have not done it. So, but it's an interesting question. It may be studied.
A simple question. What happens to your construction if you restrict yourself to self-dual Maxwell? Can you write everything in brackets and it's conformal?
Yes. So what?
For instance, you lose one of the Z would be the
Oh, but actually, from this point of view, there is conjugation. There is the way I wrote the equations. They are self-conjugate actually. I plus goes into I minus. So when Z goes into Z bar, X, yes. Actually, as I was given this 4x4 diagram, there is symmetry across the anti-diagonal. And according to this symmetry, things are symmetric. So it is the same. Yes. Okay, so quantum groups. Now, for quantum groups, I'm going back to the four-dimensional conformal case. And the form, I recall there was such a form there, where, of course, the I ones were without hats, and n plus 2 was not in quantum, in brackets. So the point here, there is a very nice property, at least for SLN. But actually, I have a paper where all the singular vectors of quantum, okay, almost all, but 100% all for SLN are given explicitly, and this is the general feature. The way you have the singular vector for the non-deformed case. For the deformed case, you just put the relevant coefficients, of course the relevant one, not this 1/2, the relevant coefficients in brackets, and this is the singular vectors of the Q-deformed SL4. And actually I should use this point to make a remark. I wanted to include this, but I didn't have space. There are multi-parameter deformations of the quantum groups. For SLN, for SL4, there is an explicit formula, and I have given explicitly this, the formulas for these multi-parameter cases. But what is important here is the following. The multi-parameter deformation of USLN, for instance, is multi-parameter only in the co-algebra sector. The algebra sector is deformed only with respect to such a Q, which means that the singular vectors are the same. What is not the same is the right action of the generators on the corresponding coset. They are all the rubbish with the many parameter centers. Okay, so, and you'll see here, the single vector is the same, very simple. And then you'll see that the right action is not, it is rather involved. Okay, but I want you to enjoy also the Q-Minkowski space-time. Actually, it's very simple. It's very simple. Very simple, and you should also have in mind that there are other deformations of Minkowski, but this is unique in many senses because it involves also terms that will vanish in the classical limit when lambda is going to 0. Lambda, oh, I'm sorry. Lambda is q minus 1. Maybe, I'm sorry that this was dropped somehow in the editing. Okay, so this is a very simple thing. The multiparameter, of course, is more, but I don't have time to show it. Of course, you have to, one has to say that for Q equal phase, the commutation relations are preserved by this antilinear evolution. The same evolution that Bernard Julien was asking. This is same evolution. The Minkowski length is invariant. The commutation relations which involve the spin variables, z bar, of course, are more involved. And again, there are terms which would vanish in the classical case. But this all is very absolutely consistent. And there, of course, is the conjugation z going to z bar, as I mentioned also in the classical case. Now, of course, we have to have representations. Now, certainly, now our variables are non-commutative variables. We cannot work with them like functions. But we can mimic many properties of the functions. So, in a sense, I will call them functions abusing the notion, but these are formal power series in the Minkowski variables. In Z and Z bar, they are polynomials because we are still insisting to work with finite dimensional Q-Lorentz representations, but finite dimensional. Okay, and now the Q Maxwell is very simple. I even give you the general, the more general, not only exactly the Maxwell, but the Maxwell hierarchy. It actually looks absolutely the same. Nothing changes. Only the content has changed. And now, namely, for instance, this right action, for instance, earlier it was just dz. Now there is this more stuff. Actually, unfortunately, the definitions are on the next page. So we have the Q-shift operators. So every variable gets shifted on the corresponding index. And we have the Q-difference operators. Certainly, for Q goes to 1, the shift goes to 1, and decay goes to the derivatives. So we can immediately see, I go back, that certainly this will go to dz, this to dz bar. Again, very crucial and very different from other people that were doing these deformations of Maxwell. We have a term which is necessary because of invariance, but will vanish when Q goes to 1 and lambda goes to 0. This is, I insist on this because it is different from what other people are doing. Okay, this we have seen. And now now the Maxwell will look, okay, a little horrible. Still, of course, you can distinguish what was there before. And certainly when Q goes to 1, of course, it will come back to what you know, but this is now the Q Maxwell hierarchy for this deformation. Okay, and certainly I have written this, but this is just the same, only the contact is very, very different. Okay, some other examples. some other examples. Q de Lambert equations. Now we have this also one parameter hierarchy which fits the overall sextet, but I choose only four representations in order to mimic the representations of the Maxwell. Although it's not Maxwell, except if R is equal to 1, because these two J's are different. These two J's are different. For R equal 1, we have some very simple Weyl equations. For R equal 2, we intersect with the Maxwell hierarchy, because in that case they coincide. And then why do we call it Q de Lambert? We call it Q de Lambert because on this representation there is this Q de Lambert equation, and you can, of course, certainly hear the Lambertian here. Of course, when Q goes to 1, this goes in dv bar dv minus d plus d minus. Of course, this is the way. This, of course, in terms of our variables x plus minus vv bar, and this here you can notice that these are really the better variables for the Minkowski space-time, because the equations are written in a more compact way. So this is this Q de Lambert equation. There is a subtlety here that it is a conditional equation, certainly because we are already in representations which satisfy this equation, and on this equation, on this, they also satisfy this Q de Lambert. Finally, something about Weyl gravity. As you know, there is something called linear conformal gravity. Actually, maybe I should have reordered the exposition. The linear conformal gravity is governed by the Weyl tensor, which is given in terms of the Riemann curvature, the Ricci tensor, and the scalar in this way. And of course, in order to linearize, of course, the metric tensor is written in this way: the flat Minkowski metric plus the plus h mu, and then the R mu looks in this very simple way. I'll go back to the other transparencies. And then the equations of linear conformal gravity are very simple. These are like this way. They have nine independent components. 9 independent components, and they are given like this. So you see, again, I'm using the bookkeeping device Z and Z bar. Okay, with Maxwell we had polynomials of second order. Here you have polynomials of fourth order. The T is a polynomial of Z, Z bar. And this is, of course, because their signatures are what we have to, what we had. Sorry that it's not written in the proper way. So now I'm actually, this thing I have from the beginning, but now I am giving you the signatures of these representations, and you can see that they have really these properties which are given a little later. Okay, and now I have, okay, there are, of course, the Weyl tensor components are given in this way. Certainly this is not very spectacular, but again, I am succeeding to write the conformal equations into a very similar way as I was writing the Maxwell ones. Of course, here the I plus and I minus, because they are polynomials of higher degrees, I have more terms. Have more terms. Okay, that's life. I didn't invent it, although I wrote it down, but that's how it works. And you can see again they can be written in terms of simplified structure. And again, of course, very important. Again, the same I1, I2, and I3, which were entered in the Maxwell, enter here, of course, in higher degrees. In higher degrees. And in higher degrees. And they correspond to, so earlier we had weights alpha 1, 2. Now we have weight 2 alpha 1, 2. Just slightly small. But of course, this makes things more complicated. And then, of course, here the small h plays the role of the potential in the Maxwell case. Also, like in the Maxwell case, we have operators going from C plus C minus. There was J mu, here it is the matter tensor, and then we had going from potential to F plus minus. Here we go from the potential to C minus C plus. And then there is a diagram which I already wrote. And then, of course, you would expect, and of course this is also true, that in the UQ case, we have these operators. Nothing more spectacular. Everything is put into brackets. Of course, we have to use the same Q-deformed operators for the simple root vectors. In fact, okay, I have spared you the final expressions because they would take too much. Yes. Okay, so I hope that you are not so exhausted, but in any case, I will stop here.
Many of your groups appear in supergravity theories, in particular n equals 2. So for instance, E7 minus 24 and minus 25, and I think E6 minus 14.
Actually, for some strange reason, people use mostly E77, which is the split form. For me, it is a mystery, but I actually plan to deal with this because by my formulas, it turns out that the same differential operators which acted for E7 minus 25 will be the same as E77. So there is place to be applied there. I'm thinking about this, but...
So I have a suggestion. I think the connection with supersymmetry you have is that in the compact group you found, I didn't follow the reasoning, but that there was an SO2 factor. The SO2 factor is the Kähler structure of the symmetric space.
Yeah.
It's also very familiar in supersymmetry or supergravity.
Yeah.
Now, for E77, it's not a Kähler symmetric space. The reason is that the definition of Kähler symmetric space is maybe too strong. There is a Kähler structure, but it's not symmetric. You see, it has to be it's connected to the accident that if you have 7 supersymmetries, you get automatically the 8th, and it's the 8th that's broken that breaks this invariance of the Kähler structure. So the Kähler structure is there, and if it's enough for you, maybe you can apply the rest of your construction. Yeah,
actually, this is of course an important point that for E7 minus 25 is a conformal algebra from my point of view. Namely, there is a SO2 factor in the maximal compact. It's not like this in E77, which maybe explains why not everything that I have can be translated, but at least that the invariant differential operators can be used. And maybe that's something.
P7 minus 25 is n equals 2 of 90. So it is Fagor-Theos.
Yes, but unfortunately, they don't use it. So, I mean, all papers that I see, they use E77, and you have papers where they use E7 minus 25? Okay, maybe I missed this. This is very important if they use directly E7 minus 25, because that will make direct relation. Yes, very good, thank you.
I would like to make a comment on the relation of the way these differential operators, intertwining differential operators, played a role in what Gerhard was telling us about the derivation of operator product expansion. The point is that group theory books give you an integral over principal series of representation, and then you have to deform the contour, and there are longitudinal measures, and there you have some kinematical poles, and it was, I think, Gerhard's idea, maybe I'm oversimplifying, that because of this special differential operator intertwining relations, they cancel the needed kinematical poles. So this was the origin. Then, of course, Vlad went much further, sort of forgot the origin of the problem, but it's good to say that it arises from the derivation of operator product expansion.
Thank you for this comment. I didn't forget, but I couldn't include in this talk because I had too much material anyway. And certainly I remember very well because I was one of those who actually calculated these cancellations. Yes. Of course, we were told by Gerhard that there should be something, but it was immediately those operators which indeed made this cancellation, which is a purely wonder because they are kinematical operators. They canceled and brought the dynamics. It was, I'm very grateful that Ivan mentioned this because the way I built my talk, I didn't have place for this, but it was very nice that he mentioned. Yes.
So I have a question about this. So I don't usually think about this Q-deformed stuff. But since you mentioned this Q-Minkowski space, I was wondering, suppose that we live not in Minkowski but in Q-Minkowski space. What is the experimental bound on the deviation of Q from 1?
You want too much from me, I don't know, sorry.
But do you know somebody studied this question phenomenologically?
Now, the only place we went into this, which I couldn't mention here, is with some students we were studying the solutions of these Q-deformed equations. And then we studied them in terms of Q-plane waves. And then in the plane wave, it appears so that things which are in the denominator of propagators, like p squared minus m squared, for instance, or just p squared, they appear in the solution of the plane waves in the denominator. And what is very important is they split. You see, we don't have quadratic, we have, say, p minus something times p minus something else. So, which means that the singularities are smaller. They're not quadratic, they're linear. In fact, this was proposed by Majid that it may happen. He never worked it out, but we have it in our papers. So this is where we enter physics, maybe in some way.
Just a very obvious comment to your question. I mean, Q is e to the I h bar. divided by some action or some angular momentum. So if you want the effect to be important, you want a very small action, very small angular momentum. So,
Okay, thanks. Thanks again to Vladimir, and we are adjourned for a coffee break.